Mountain landscapes emerge from the interplay of multiple competing processes, from erosive to tectonic forces. By modeling these physical processes, terrain simulations aim to generate plausible, consistent, and diverse synthetic landscapes. We focus on the role of momentum conservation in terrain evolution. This fundamental principle drives the emergence of characteristic landforms such as meanders, deltas, braided rivers, and debris deposits. Modeling momentum conservation is challenging, because geomorphological processes operate across vast timescales. Landscapes evolve through erosion over thousands of years, while the motion of water and debris occurs over seconds to days. At the erosion timescale, transport can be considered instantaneous. Yet, its cumulative effects shape long-term structures, such as river networks, or deposits of sediment and debris. To capture these long-term effects, we introduce the concept of geomorphological transport, and propose a new particle-based algorithm to simulate it efficiently. For example, river flow originates from upstream precipitation. We sample precipitation at random locations, propagate it downstream, apply attenuation, and accumulate its contribution to the river volume. This algorithm is parallelizable and simple to implement. Despite its simplicity, we show that it accurately enforces physical conservation laws. Using this framework, we introduce a new erosion model that explicitly accounts for momentum conservation, leading to a wider diversity of landforms. Here, we uplift an isolated mountain. Debris flow erosion forms steep slopes and leaves characteristic scar patterns. Rivers concentrate in the main valleys, and form evolving meanders as they carve through debris deposits. Note that we use a lighter shading to highlight the deposit locations. Next, we design a mountain range and modify the precipitation map to increase rainfall on its windward side. This reproduces a common meteorological phenomenon known as the orographic barrier. Viewed from the leeward side, debris-dominated erosion produces landforms typical of dry regions, such as deposition terraces, mesas, and canyons. Finally, we reduce the physical scale to focus on the formation of a single valley. Here, deposition and erosion from debris flows compete to shape the mountain slopes. In depositional areas, rivers oscillate rapidly, forming evolving meanders and braided patterns that progressively widen the riverbed. We now isolate the effect of momentum conservation on river dynamics. In this example, uplift and rainfall from upstream feeds a basin with water and sediment. High deposition coefficients favor the emergence of braided patterns and deltas. Reducing deposition leads to the formation of meanders and associated features such as oxbow lakes, cut banks, and scroll bars. On the right, we disable momentum, and these effects disappear. Momentum conservation is also essential for forming characteristic debris fans at the base of steep slopes. Without momentum, deposits become smaller and unrealistically steep. We compare our approach, shown on the left, to previous methods based on the stream power law. The footage in the middle uses momentum-based transport but replaces our erosion model with the classical stream power formulation. This highlights the advantage of our approach, which produces greater variability in mountain and valley structures. On the right, we compare with previous implementations where rivers follow the steepest descent direction, which suffer from strong directional artifacts. The framework also naturally extends to additional processes. This is illustrated here by the inclusion of a lateral force which mimics the formation of a dune field. Thank you for watching.